So this is something that's a little bit close to my natural habitat. So I wanted to talk here about some background mathematics, namely here the mean and variance of linear functions. So in finance it's often helpful to use the mean to represent the expected return and the variance or standard deviation to represent risk. So there are sometimes other better ways of representing these things, okay, but usually the easiest way to do this is to use the mean to represent the expected return and the variance or standard deviation to represent risk. So if you're given the mean and a variance of a random variable x, say, it's often useful to calculate the mean and the variance of a linear function of x for constants a and b, precisely because in the financial setting the mean would represent the rate of return and the variance would represent the rate of risk. Okay, so the basic way to remember this is that the mean is linear but the variance is quadratic. So if you look at the first equation on the slide, I'm not going to talk you through this, but the thing to get from this, that this essentially works in a linear way, so the mean is linear. Now the second one, you can ignore the b bit and it's just concentrate on the a bit. The variance, the second equation here, is quadratic. So I want to give you some numerical examples of this. So the term linear function can look a little bit complicated, but it really isn't. So you're given an example in the first part of the slide. So if x is Poisson distributed with parameter 10, what is the mean and variance of y equals 3x plus 10? So all you would do is take a equals 10, b equals 10. The fact that x is Poisson distributed with parameter 10 means that the mean and the variance are both equal to 10, and then the expected value of 3x plus 10, as the first equation shows, could be calculated to be equal to 40. This just ends up being 3 times 10 plus 10 in this case. And then for the variance of 3x plus 10, you can ignore the 10 bit, and the coefficient of x, 3 here, is squared because the variance is quadratic. So in this case the variance of y should be 90. And then more abstractly, if you've got different numbers other than 3 and 10, it should just work exactly the same way. Sometimes there might be some algebra. So there we've got y equals mx plus c, but the same process works again. So the mean is linear, so the mean of y would just be m lambda plus c in exactly the same way as the first numerical calculation on the slide, and the variance of y is quadratic, so this will be m squared of lambda, exactly the same as above. Okay, so back to the model then. So I promise you that this is a very simple model, but it is intended to try and say something useful about the context of value creation. So suppose the number of sales is Poisson distributed with some parameter lambda, and suppose you have a target gross profit of, say, £T. Suppose you have a margin M on each item sold. How many items should we make and sell in order to hit our target gross profit of £T? And then the next point here is that what is the associated variance of the gross profit? So this is a very simple mathematical model which is aiming to abstract from some fundamental principles of value creation. Now the point that we're trying to make with this model is there's potentially two ways of operating, either a high volume low margin or low volume high margin. Now you could manipulate both these things in order to hit a profit target, but it turns out that in a certain sense a low margin high volume model is thought to be less risky. Okay, and we're going to quantify this by looking at the variance that we did some calculations for earlier. Okay, so in terms of the solution to the first question then, so in terms of how many items should we make in order to hit our target gross profit, so you assume, for the sake of simplicity, that every item you make you sell. So if you sell X items, you make M profit on each item, so the gross profit would be equal to M times the number of items sold, so in this case MX. So what you've got here is just some sort of high school algebra, but this is almost designed to look harder than it really is. So the expected gross profit then is given by the expected value of mx, so the mean is just linear. So what you have in this case, that the expected value of mx is just equal to m times the expected value of x, so equals to m lambda on this case. So in order to meet this target, what you have to do is set t equals to m lambda. So t is the target that's been set. M, you may not have much control over, is the amount of profit you make on each individual item. Lambda, the number that you make and sell, is the thing you can control. So set t equals to m lambda, solve for lambda, and you should have here that lambda equals t over m. Okay, so this means that if you want to hit this profit target, you need to construct t over m items. So alongside this, you want to calculate the variance of the gross profit. So the gross profit is equal to m times x. The variance is quadratic, so the variance will become m squared times the variance of x, so m squared lambda. Now, when we did the previous calculation on the last slide, we had that lambda equals t over m in order to meet this sales target. So in this case, the variance of the gross profit would be equal to m squared times lambda, so m squared times t over m, which would come out as m times t. So the point of this is that since the variance of the gross profit is equal to m times t, as m increases, the variance of the gross profit increases as well. Okay, so as you increase m, the risk of the whole thing also increases. So the point of this is that this is just a simple observation. It's just high school algebra really. Okay, but the implication is that the higher the margin is on each item, potentially the more risky it is in terms of hitting this original sales objective. Okay, so if we're looking at the implications of the model then, so the variance of the gross profit is equal to mt. So as the margin m required to hit the profit margin increases, the variance of the gross profit also increases. So this means that as m increases, the risk increases. So the striking implication of this admittedly absurdly simple model is that having a large number of small margin transactions actually seems to be less risky. Okay, so there's two basic ways in which you can try and formulate your business and create value. You can have a model where you have low margins and high volume, or high margins and low volume. And the implications of this model would be that if you have a model which seems to be more simple, where you have low margins and high volume, there's a certain sense in which this seems to be less risky. Now I think this probably still continues to hold in the present day with respect to fintech applications, but I think there are potentially at the moment some difficult questions to ask in terms of physical customer facing models, where that has become problematic in light of the social restrictions during the coronavirus crisis. So in summary then, just to recap what we've talked about during this lecture, so historically technology has provided value by reducing the cost of products and services and trying to expand the size of the market of potential customers. So again, as we said before, trying to think of new technology as fundamentally serving as a democratizing process. What you're trying to do is make something available to everybody, and in so doing, the value you're creating for your business is trying to expand the size of the market of potential customers. In this last part of the lecture, we've discussed a very simple mathematical model, and it was really as simple as I tried to promise you. As part of this though, I think there's certain things and certain areas of economics and finance that really you can't understand properly unless you explore them in quantitative and numerical mathematical terms. And the point of this model here was that given two choices of possible business model, infrequent transaction with large margins or frequent transactions with small margins, there's a certain sense in which the second option actually seems less risky. Okay, so I suspect that this way of working will continue to hold true for fintech applications, but it might change slightly in the light of the current coronavirus social restrictions. So I just wanted to emphasize at this juncture that there are certain reasons for caution within this subject of value creation. So firstly, as we've seen in other parts of this lecture course, the importance of a historical perspective. So even if we're interested in new financial technologies, you still can't ignore some of the important lessons from history, and indeed it can be surprising just how useful some of these lessons are, given how far back in time you might be going. The second subtle point here is I think the importance of getting the entrepreneurial balance exactly right, and this may be something that it is difficult for academics to precisely advise upon. Another thing I wanted to talk about here is the economics of appropriation. So as we've discussed before, again, if you look at the historical record, all sorts of examples where technological innovation was not accompanied by commercial success. Another thing that is often ignored in fintech is this issue of regulatory risk. Whole books have been written on this, and then as we've seen, for example, the recent coronavirus crisis, you need to be aware of black swans, so something that can just arrive completely unpredictably, which changes everything. Okay, as we've seen, that's affected whole swathes of society over the last 10 months. Okay, so in terms of a historical perspective, referred to this classical text by Reinhardt and Rogoff before, just be aware of this time is different syndrome. So even if we're interested in new financial technologies and new markets, history gives perhaps the best, albeit imperfect, way of understanding the present. And I think of all the perspectives, historical perspective is likely to remain relevant the longest. Throughout human history, the belief has been held that financial crises are things that happen to other people in other countries and at other times. So misguided beliefs which have confused people when it comes to this issue of value creation in the past include: we are smarter, we have learned from past mistakes, old valuation rules don't apply, our new WYSI payment system can't be hacked. Okay, so you share an awful lot in common with ancestors. You're likely to be sort of smarter. There's evolutionary stable preferences for risk, return and greed, etc. It's difficult to learn from past mistakes. Old valuation rules may still apply in the context of financial technologies. That's one of the lessons of the internet bubble at the turn of the millennium. And historically, an important issue is that payment systems can be hacked in unforeseen ways. So it's important, I think, to reflect upon this, that it's difficult to get the entrepreneurial balance exactly right. So in any academic study of blockchain and fintech, it's easy to advise caution, and two core ingredients here would be the dangers of speculation and excessive hype, and regulatory ambiguity. Now when you do a course like this, inevitably you're taught by a finance academic, and academic finance is fundamentally about balancing risk and return. I suspect that practitioner finance is essentially the same thing on top of that. But because academic finance places such an emphasis on this interplay between risk and return, the personality profile of most finance and economics academics is likely to be quite highly risk averse. That's certainly true for your uncle, Dr. Fry. Now, risk aversion may be a great quality for finance and economics academics, but risk aversion may not be a great quality for fintech entrepreneurs. So certainly when it comes to value creation and fintech, I think that some things are inevitably unknowable and uncertain, and this will feed forward through to the issue of black swans mentioned earlier. So a degree of risk taking may be needed, and that might suit certain personality profiles better than others, but probably should have a calculated gamble rather than a leap in the dark.